Hello and welcome back to Real Analysis. And as always, first I want to thank all the nice people that support this channel on Steady or PayPal. Today we talk about the pointwise convergence and the uniform convergence of a sequence of functions. Here please remind yourself that we have already learned in the last video what a sequence of functions is. For all indices n, we get a function fn that has the domain I. And now such a sequence can have a convergence property we call pointwise convergence. It's a very natural notion because you immediately get it when you know how to deal with sequences of numbers. That is because for all the functions here you can fix a point x tilde and you get an ordinary sequence of numbers for the values of the functions. And if this is a convergent sequence, we can define a limit function and call the sequence of functions pointwisely convergent to this function. And for the name for this limit function we can just choose f. Hence what we need here is that no matter which x tilde we take from I, we get a convergent sequence here for the values. And then the limit we just call f of x tilde. So you see, the important part here is that we have this property for all x tilde. Therefore, it might not be so surprising that we can describe the whole thing efficiently by using quantifiers. So for all x tilde in I, we have the convergence property. Hence for all epsilon greater than 0, we find a capital N, such that for all indices afterwards, we have that the absolute value of the sequence member fn x tilde minus the limit is less than epsilon. And this is exactly what you can remember for the pointwise convergence of a sequence of functions. It just means that all the vertical slices here in the graph are convergent sequences. So I would say let's look at an example. There we just need to look at a sequence of functions. Here the domain I should be just the interval 0 to 1. And the function fn should be defined as 1 over n times x plus 1. So you see, this is a very simple example because the graph of f1 is just a straight line. And of course f2, f3 and so on are also straight lines. And when we draw all of them, we see that the steepness gets less and less. Hence the graph of the limit function should be this horizontal line. Of course, we also can immediately calculate this by just fixing a point x tilde and looking what happens. So for fixed x tilde, here we have our sequence of numbers and we immediately see this is 1 over n and this is a sequence that is convergent to 0. Hence by our limit theorems the whole sequence goes to 1. This happens no matter what x tilde exactly is, hence our limit function is the constant function. To be more concrete, we should call it the pointwise limit function f. So you see, this was a simple example where the calculation was very short. Therefore, the next example should be a more complicated one. So let's take the same domain as before, namely the interval 0 to 1. However, now the function is defined piecewisely, where the first case is n squared times x times 1 minus nx. And now this is important, this case is defined for the interval 0 to 1 over n. Hence this interval here is also dependent on n. Now the second interval is therefore just 1 over n till 1. And there the function is set to 0. Okay, now the first thing you should do is to look at some graphs. Here on the x-axis we have the interval 0 to 1 and we find 1 over n somewhere in between. Here the example is of course the case that n is equal to 2. Then we know on the right hand side we just have the value 0. And on the left hand side we have a parabola where we also know the zeros. Hence the result looks like this. Please note that we also know that the maximum value here lies at the point 1/2 times 1 over n. Therefore we can immediately calculate this value. So let's put this point into the function and then you see we can cancel out a lot of n's. So what we get is n over 4. This means that the maximum here increases with n. Hence the next function in our sequence would look like this. Obviously the region where it is 0 is larger, but the peak of the function is also higher. And then you can imagine what happens when we continue increasing n. Of course, now the question is, do we have a pointwise limit function? The answer is yes, and you can also see it in the picture. Just fix a point x here, and then you see at some point when n is large enough, this value is at 0. For writing that down, we should distinguish two cases. The first one is the simple one. X is equal to 0 means the value of this function at this point is equal to 0. And this property holds for all n. Now the case that x is greater than 0 gives us also the value 0, but only in the case that n is large enough. Of course, this is not hard to check. This is exactly the case when n is greater than 1 over x. Because then x lies in this interval here. Or in other words, on the right hand side here where the function is 0. Now we can reformulate the whole thing by saying the sequence of numbers f and x is constant eventually. Therefore it's also convergent with limit 0. Hence we have a pointwise limit function given by the 0 function. So you see, the result is that we have convergence for the sequence of functions, though the values of the functions get larger and larger. This is a strange result we didn't have for just sequences of numbers. This tells us that the pointwise convergence is maybe not strong enough for our needs. This gets even more apparent when we look at the following example. Imagine that we have the following graph of a function. It's not so complicated, so it's constant, linear, and constant. However, you see there are no jumps in the function. Now the next function in the sequence should look similarly, we just push it a little bit to the right here. Hence the linear part here gets steeper. And then you can imagine how we continue the whole sequence. Also you should see with this picture, when we go to the pointwise limit, we get this function. So we get a function with a jump. Although we started with a whole sequence of functions without jumps. And that's indeed a good reason why we want a stricter convergence property. One that does not allow such strange results here. Indeed, this is what we call the uniform convergence. Now, the definition and examples for the uniform convergence we will do in the next video. So I hope I see you there and have a nice day. Bye!